Hi everyone, welcome to part 2 of section 12.2. In this video, we're going to be focusing on the third bullet point. So by the end of this video, you should be able to calculate and interpret what is called the coefficient of determination. So let's just start off with a quick recap. The objective of regression, we said earlier, is to examine and evaluate possible relationships between non-deterministic variables. And here's an example that we considered earlier: hours of exercise versus percentage of body fat. Now in practice, you're going to draw a scatter plot like this one, and then you'll have a look to see, can you now put a line through your data set? If you see some other kind of pattern, maybe a curve, then you might want to try a different kind of regression. So in this case, we can see the data seems to lie around a line of some sort. And this line, we call it the true regression line. So it's supposed to be the true relationship between the variables y and x. But we know that in reality, all of these points don't necessarily lie on the line. And the reason for that is that there's going to be other factors that may have a role in affecting the relationship between y and x. So if you consider this example here, suppose you have your hours of exercise, which is x1, and then your percentage body fat. You can see it's not perfectly on a line, this person's point here. And this variation here, which is not accounted for by this line, could come from other factors such as a person's age. It could also come from a person's gender, because we know that the percentage body fat in a female is different to that of a male and even across different ages. But this regression line does not account for that bit of variation. So that's how you end up with points around the line. So now that you have this true regression line, you will now want to estimate it. Remember, these are population parameters, so you don't know the true values. So you'll take a sample and then you'll estimate the parameters, and you'll be able to come up with an estimate for that true regression line. So we covered earlier how to find estimates for beta hat 0, beta hat 1, and sigma hat squared. Now we want to focus on this SSE term. That is the basis of the coefficient of determination, and I will explain to you in the upcoming slides how you can interpret values that you get of SSE. Now here on page 632 is where the whole story about the coefficient of determination begins. So we're going to start off with this formula for SSE. And remember, this is given in your formula sheet. You don't need to memorize it. The important thing is now the interpretation. SSE measures the amount of variation in y that is left unexplained by the linear model. So I'll explain that in a little bit more detail just now. But if you look at this graph, if you were to try draw a straight line, all the points would lie on the line. And remember, just now I was explaining that the points will lie off the line because there's other sources of variation that are not y. But in this case, you can see that, that are not x. So in this case, you can see that all the variation in y, that means every single value of y here, can be explained by x. As long as you know x, you'll immediately know what y is. So there's no variation that is not accounted for by this model. So in this example A, you'd expect SSE to be equal to 0. Okay? And then in the second graph, if you try to draw a line, you have something similar to the first graph. Some of the variation is not really explained by the model because some of the values lie off of the line. So you end up with an SSE that is not equal to 0. And then in case C, here it's not so clear what the regression line would look like. So in this case, you expect that the regression model will explain very, very little of the relationship between the variables. Let's have a closer look at the formula so you can see where this interpretation comes from. So consider the scatter plot given here. And the formula says we take yi, which is the point that you've observed, and you subtract y hat I. That is the estimate from the line. So that is this point. Then SSE takes the difference between the 2 points and squares them. So it's that. So remember, that's also how you calculate a residual. So sometimes SSE is also called the residual sum of squares. So you're summing this. And remember, I was telling you earlier that these points don't lie exactly on the line because there are other sources of variation that are there. So I gave the example of the person's gender or person's age. Remember, this line is only for the body fat percentage and the person's weight. It doesn't account for other things. So that means if you take this difference here, that is variation due to other things. In other words, that is variation in Y that is not explained by this linear regression model. Now there is another sum of squares that is of interest. It's called the total sum of squares. So the total sum of squares is given by this formula here, and it tells you the total amount of variation in the observed variables. And the way it's calculated is it takes yi minus y bar. So if you look at it visually, yi is these points, like we said, the observed ones, and then y bar is just the average of your points. So now if you take the sum of the squares of these differences and you just take all of them, then that is actually going to give you the total amount of variation in the observed y values. So what does that mean? Now we can actually talk about proportions here. You have the total amount of variation and you have what's unexplained. So if I wanted to define the proportion of the variation y that is left unexplained by the linear model, I would just take SSE over SST. And then, now if I wanted, like, if you think of it as the opposite or the complement, or in other words, the proportion of the variation in y that is explained by the linear model, then you'd simply say 1 minus SSE over SST. And this value here, 1 minus SSE over SST, is what is called the coefficient of determination. And this is exactly the interpretation. So if ever you're asked in a test or an exam to interpret the coefficient of determination, then you're going to say that it is the proportion of variation in y that is explained by the linear model. So the formula is given on page 634, and we usually denote the coefficient of determination by the letter r squared. Okay, and there's a special reason why we use r, and we're going to look at that in 12.5. So remember, we used r in first semester for the correlation coefficient. So there is a relationship between these two things, and we'll do a recap a little bit later. So this is just something for you to remember. Now, I just want to give you a few points to remember. So let's start off with the first one in terms of interpretation. Okay, so remember we said that the coefficient of determination tells you the proportion explained by the model. So you can also look at it this way. The higher the value of r squared, that means the more variation that's explained by the model, the more successful the simple linear regression model is in explaining the variation in y. The second point that you need to remember is that r squared is always a value between 0 and 1. And that makes sense. Remember, r squared is even a proportion. It is sometimes given as a percentage, and you know that's also going to be between 0 and 100% as well. So if you look at this example from your textbook, example 12.10, which is a continuation of 12.5, if you calculate the r squared, so your coefficient of determination, this is the value you'll get. So you can go and verify that in your textbook. You'll get 0.882. So the interpretation in this case is that 88% of the variation in y is explained by the linear model. And now to point number 3. SST can be split up into two parts. Okay, so remember SST, when we found SST is equal to SSE plus SSR. SSR is called the regression sum of squares. And you'll see just now where exactly this comes in. So remember we said this is the definition of r squared, which is 1 minus SSE over SST. And then if you know that SSE would be equal to SST minus SSR, so just rearrange this formula and put it in place of SSE, you would end up with SST minus SSR divided by SST. Okay, so it's just substituting SSE in there. And then if you now bring everything under the same denominator and you simplify everything, you end up with SSR over SST. So this is actually just another way of calculating your coefficient of determination. So suppose instead of being given SSE, you are given SSR, then you can use it to calculate your coefficient of determination. Or if you have this formula and you have SST, you can use it to calculate SSE. This formula, I don't think it's usually given in your formula sheet. So this is something that you probably might have to memorize if you do need it. Okay, so now let's have a look at an example. This is exercise 20. You had to do A to C. In this one, you need to be able to do D, and they give you this output. Um, this output is from, it's typical statistical software output, even though you're not doing this particular software, you'll get output like this in most packages. So in this case, they calculated r squared, and you need to be able to interpret it as well. And in this case, if you calculate SSR over SST, so they give you the regression sum of squares, which is at 1.0427, and then divided by SS total, you'll get 0.717. So in other words, you can say 71.7% of the variation is explained by the model. So that brings us to the end of this section.